Did you ever wonder how does a calculator compute for the value of the sine function? Most functions can be approximated by polynomials. And to compute for sine of x, a calculator would evaluate such a polynomial. Most calculators use something we call as the Taylor series or Taylor polynomial. And a special case of Taylor polynomial is what we call as the Maclaurin series. And on your screen, you can see the Maclaurin series approximation of the sine function. And in this lesson, there are two things that we would like to accomplish. First, we would like to understand what does this series of terms mean? And number two, we would like to know how do we arrive at the formula and why does the formula work? So let's begin by visualizing this Maclaurin series of sine of x. So we are going to go to Desmos graphing calculator. So we are now here at desmos.com graphing calculator. The curve that you can see on your screen is the sine wave. And what we are going to do is we are going to superimpose the terms of the Maclaurin series of sine of x to the graph of sine of x. And let's see what happens. Let's begin by putting in two terms. So this blue graph now is the graph of x minus x cubed over 3 factorial, which are the first two terms of the Maclaurin series for sine of x. Let's add one more term to make it 3 terms. And you will notice now that at this middle part, the graph of the sine of x and the graph of our series coincide. The series is hugging the graph of the sine of x. Now let me add another term to make it 4 terms. And you will notice that the graph again at the middle is coinciding with the graph of sine of x. Then let me add some more terms. And you will notice that the blue graph expanded going to the right, but every time it expanded, it traces the graph of the sine of x, which is the red function. Let me add several more terms. Notice now that as we keep adding terms to the Maclaurin series, the graph of the sine function, which is the red graph, and the graph of the series coincide. Now from the interval between -6 to +6. Now let me add some more terms. This time I'm adding up to the 23rd power. And you can see now that most of the red curve are covered by the blue graph. Let me zoom out a little so you can see what's going on. So that's what's happening in this graph. If I added only one term, I have this line. When I added 2 terms, the curve is being traced by the blue graph. When I added 3 terms, the blue graph is approximating the red graph. And as I keep on adding terms, the interval in the graph where the red and the blue graph coincide expanded, so that if I added a lot more terms, the interval where the blue and the red graph expanded, and now you have this zoom out version of the 2 graphs. So this is now what we mean by the sine function approximated by a polynomial in the form of a Maclaurin series. And you will notice that in here, I only stop at x raised to the 23rd power over 23 factorial. If I continue expanding this up to infinity, then this blue graph and this red graph would coincide infinitely. And so we now say that the sine of x has a corresponding Maclaurin series representation. So how does the Maclaurin series work and why does it work? Let's do some investigation. Let's begin with something that you are already familiar with. In our video number 31 about geometric sequence and series, we already derived this formula for the sum of the terms of a geometric sequence, which we call as the geometric series. And the geometric series converges if the common ratio r has this property. The absolute value of r is less than 1, meaning the interval of our r value is from -1 to +1, open interval. -1 and +1 are not included. So from this geometric series formula, let a be equal to 1 and r be equal to x. So we're going to replace this a with 1 and this r with x. And we will arrive at this result. Everything else are the same except that instead of A, we replace it with 1. Instead of R, we replace it with X. And so every time we see A, we now have 1. Every time we see R, we now have X. And from this form, we can now represent our geometric series as a function of X this way. F of X is equal to the summation of X raised to N is from 0 to infinity equals 1 over 1 minus X. So what happens here is our formula for the series A over 1 minus R is now replaced by 1 over 1 minus X because our A is 1 and our R is X. And this can now be represented as a function of X, f of X, equals 1 over 1 minus X. So this is now our representation of a geometric series. A is common to all the terms that iterate from n equals 0 up to infinity. Now, if this A is no longer constant, meaning the coefficient of every term could vary, and we call that C sub n, then what we now have here is what we call as the power series. Notice that the only difference between the geometric series and the power series is the coefficient A and C sub n. Here, A is common to all the terms in the series, whereas here, C sub n vary depending on the index, and the index starts with 0 up to infinity. The power series also can be centered at certain constant A, and if A is 0, then we have that special case that we saw in the previous slide. But when the center of the series is not 0, then we have this binomial x minus a raised to n instead of x raised to n. Everything else are just the same. Now let's expand our power series from n equals 0 up to infinity. So our form would be like this: c sub 0 times x minus a raised to 0. And that would be equal to c sub 0 because x minus a raised to 0 is 1. And 1 times c sub 0 is c sub 0. For n equals 1, this becomes c sub 1, and this exponent becomes 1. So you have the quantity x minus a raised to 1, which is now this part. When n equals 2, this becomes c sub 2, and this exponent n becomes 2. So we have the quantity x minus a raised to the second power, which is now this term. When n equals 3, this becomes c sub 3, and this exponent becomes 3. So you now have the quantity x minus a raised to the third power. And then we continue the pattern up to infinity. And that is represented by these 3 dots. So this is now the polynomial expansion of this power series. And the main question now is, what are the values of these coefficients? C sub 0, C sub 1, C sub 2, C sub 3, up to C sub n. And once we find the pattern with these coefficients, plus the pattern that is very apparent with the binomial raised to iterating powers from 1, 2, and 3, then we can have an idea of what is the exact expansion of this power series. So let's start by finding what is the value of c sub 0. To find c sub 0, let's evaluate the function at x equals a. So instead of x, we replace it with a. Instead of x, we replace it with a, and do the same thing for the other instances of x. And so we now have this part. But notice here that you have a minus a, which is 0. So this is 0. This is also 0. And this is also 0. And 0 times any coefficient would still result to 0. So in effect, everything here would be 0, including this part. And what is left is c sub 0. What we now have, therefore, is f of a is equal to c sub 0, and all the rest are zeros. So we know that f of a is equal to c sub 0, which now gives us the value of c sub 0. C sub 0 is equal to f of a. So going back to the expansion of our power series, we already know the value of c sub 0. C sub 0 is our f of a. Let's now focus on c sub 1. What is the value of c sub 1? What we're going to do here in order to find c sub 1 is we're going to use the first derivative of f of x. And the differentiation here is not that difficult because all we have to do is apply the power rule. The power rule says that if you have f of x in the form x raised to n, then the first derivative of f is computed by putting this exponent to the front and then subtracting 1 from the exponent. So, what is the derivative of c sub 1? The derivative of c sub 1 is 0 because the derivative of a constant is 0. What is the derivative of this? C sub 1 is a constant that we can factor out, but you now have this x minus a raised to the first power, which is in the form like this, where our n is 1. So if you put 1 at the front and copy x minus a and subtract 1 from the exponent, that becomes raised to 0. If we apply chain rule, the derivative of x minus a is 1, so we don't have to worry about that anymore. But the quantity x minus a raised to 0 is 1. Therefore, 1 times 1 is equal to 1. So the derivative of this part is 1 times c sub 1. So we have this c sub 1. Now for the derivative of this part, we put this exponent to the front. So you have 2c sub 2. We copy the base, x minus a, and we subtract 1 from the exponent 2 to get exponent 1, times the derivative of the inside function, which is also 1, and it does not affect the computation. And then for the next term, to get the derivative of this part, we put this exponent at the front to get this 3, copy c sub 3, copy the base, and then subtract 1 from 3 to get 2, times the derivative inside, which is 1. And we now get this term for the derivative of this part. And then, once we have this derivative, let's evaluate f prime of a. So replace all instances of x with a, all instances of x with a. And notice that you will have 0 here again. This would be 0. This would be 0 again. And this is 0. So what is left is f prime of a would be this c sub 1. So therefore, f prime of a is equal to c sub 1, and we already achieved our goal of finding the value of c sub 1. We know that c sub 1 is equal to f prime of a. So far we already found the value of c sub 0, c sub 1. C sub 0 is f of a, c sub 1 is f prime of a. The next goal is to find what's the value of c sub 2. Let's go back to the first derivative that we arrived at in the previous slide. At this time, let's get the second derivative of f of x, and that is denoted by f double prime of x. And to get the second order derivative of f of x, all we have to do is get the derivative of the first derivative. So let's differentiate f prime of x. And let's do that term by term. The derivative of 0 is 0. The derivative of a constant c sub 1 is 0. Here, the derivative is computed using the power rule with our n equal to 1. If we subtract 1 from this exponent, we get 0. Any number raised to 0 is 1. So what we will have here is just 2c sub 2. And then for this part, we can put this exponent 2 to the front as factor. So you have 2 times 3 equals 6. Then c sub 3. And then subtract 1 from exponent 2 to get exponent 1. And then copy the base. And then get the derivative of the inside function, which is 1. And then here, you have this 3 multiplied by 4 to get 12, and then copy c sub 4, get the derivative of the quantity x minus a raised to the third power, which is the quantity x minus a raised to 3 minus 1, which is 2, times the derivative of the inside function x minus a, which is 1. This is now our second derivative. And then let's evaluate again the second derivative at x equals a. So at x equals a, we replace all instances of x with a, and this part now becomes 0. This part becomes 0. These two are zeros. So what we have is 2c sub 2 equals f double prime of a. And solving now for c sub 2, we can divide both sides by 2 to get f double prime of a over 2 equals c sub 2. So this is now our representation. So this is now the value of c sub 2. C sub 2 is f double prime of a over 2. And we can now see some pattern. You have f of a, f prime of a, f double prime of a over 2. So for c sub 3, it appears like we are going to get f triple prime of a, but we do not know what is the denominator. So let's compute for that. Let's begin again with the second derivative, and let's find the third derivative. Let's begin again with our second derivative of f, which we already computed a while ago. And this time, let's get f triple prime of x, or the third derivative of f of x. And we can do that by simply differentiating the second derivative. So the derivative of 0 is 0, the derivative of 0 is 0. The derivative of 2c sub 2, which is a constant, is also 0. And the derivative of this term is 6c sub 3. And the derivative for this term would be this exponent 2 times 12 to get 24, copy c sub 4, and then subtract 1 from the exponent 2 to get exponent 1, and continue the pattern. Next, let's evaluate f triple prime of x at x equals a. So every time we see x, we replace with a. And this part becomes 0. So this entire term would be 0. So what we are left with is f triple prime of a equals 6c sub 3. And computing for c sub 3, we can divide both sides by 6. And we now have this expression for c sub 3, which is f triple prime of a over 6. So let's look at now the pattern. The pattern is f of a, f prime of a, f double prime of a over 2, and f triple prime of a over 6. How are we going to represent this pattern in the denominator? Notice that this 6 can be written as 3 times 2 times 1, which is just the same as 3 factorial, which is now this 3 factorial. So when you have triple prime, you divide it by 3 factorial. When you have f double prime, we divide it by 2 factorial, because 2 factorial is 2 times 1. And by definition, 1 factorial is equal to 1, and 0 factorial is also equal to 1. So in effect, we can now complete the pattern. You have 0 factorial, 1 factorial, 2 factorial, 3 factorial. And you have f, f prime, f double prime, f triple prime. So the exponent agree with the order of differentiation and with the denominator factorial. And so we can now come up with a formula. Our formula now for the expansion of the power series is the summation from n equals 0 to infinity of fn, where n is the order of differentiation, at the constant a over n factorial times the binomial, the quantity x minus a raised to the n power. This series now is what we call as the Taylor series of a function at a, or f centered at a. And this is now the series that is programmed in the calculator, the reason why we have the expansion of sine of x. And a special case of the Taylor series is when a is equal to 0. That means the function is centered at 0. So let's take a look at the difference between the Taylor series and the Maclaurin series. Notice that the Maclaurin series is just a special case of a Taylor series, and when a equals 0 for the Taylor series, what we have is what we call as the Maclaurin series. So let's focus ourselves on this Maclaurin series. So for the Maclaurin series of sine of x, what we are going to do now is to expand sine of x using now this Maclaurin series formula. You have the summation from n equals 0 up to infinity of f to n prime of 0 over n factorial times x raised to n, where our f of x is sine of x. And using the Maclaurin series, what we need is f of 0, f prime of 0, f double prime of 0, f triple prime of 0. And for this expansion, we need to compute for f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and so on. So our f of 0 is sine of 0, because our f of x is sine of x. So what's the value of sine of 0? So let's recall our unit circle. An angle of 0 degree or 0 pi radian is at this point, and the coordinate at this point is x equals 1 and y equals 0. And in the unit circle, the x coordinate is your cosine and the y coordinate is your sine of the angle. So the value of sine of 0 is the y-coordinate at this point, which is 0. That's why sine of 0 is 0. Now, what is the first derivative of sine of x? The first derivative of sine of x is cosine of x. And if we evaluate cosine of x at 0, we have cosine of 0, which is equal to 1. That's why we have this. The second derivative of sine of x is the derivative of the first derivative, and the derivative of cosine of x is negative sine of x. Evaluated at x equals 0, we have sine of 0, which is 0. So negative of 0, still 0. And for the third derivative, we're just going to get the derivative of the second derivative. So the derivative of sine of x is cosine of x. We just copy this negative sign. And the cosine of x evaluated at x equals 0 is 1. And then we copy the negative 1. And after these first 4 terms, we are just going to repeat the cycle all over again, every 4 terms. And that makes our expansion a little bit easier to follow. So using now these values in yellow, we now have this result. So this part here is now this part. This second term is now this second term here, and so on. Notice that this part would just be 0. This part here would also be 0. And this part here would also be 0. So what we are left with are these terms. And so this is now our result. This is 0. This is x. This is 0 again. This is negative x cubed over 3 factorial. This is 0 again. This is x to the 5th over 5 factorial. And continue the pattern. And then removing now all the zeros, what we are left is x, negative x cubed over 3 factorial, plus 5 over 5 factorial, and so on. And if we follow that pattern, we now arrive at this Maclaurin series expansion of sine of x. And this is the polynomial that we use when we graph the approximate polynomial for sine of x. And we can now summarize this series using sigma notation. Either we start at n equals 0 or n equals 1. But these two formula are equivalent. Notice that if we start at n equals 0, that means this is index 0, index 1, index 2, index 3, and so on. At n equals 0, using now this first formula, we have negative 1 raised to 0 times x raised to 2 times 0 plus 1 all over 2 times 0 plus 1 factorial. Any number raised to 0 is 1, and 2 times 0 is 0, so you are left with 1 factorial, or simply 1, and this is equal to x, which is now this x. And you can verify these other terms by using this formula. Either you use the first formula or the second formula, you'll verify that you'll generate this series using this. And this is now what we call as the Maclaurin series of sine of x.